Test for goodness of fit, chapter 11. Okay, this example, we have a stem plot of 50 birth weights. So we have the 4 in row 5 is 54-ounce baby, 7 in row 6 is a 67-ounce baby. We have two numbers in row 7, 72-ounce baby and a 75-ounce baby, and so forth. Altogether, there's 50 birth weights here. And the mean is 105.6 ounces, standard deviation 19.1567114 ounces. You can get those if you put these in the calculator, but I'm giving those to you because I'm not trying to focus on, at this point, on those computations. So with 95% confidence, we want to test whether the birth weights are uniformly distributed on the interval from 50 to 149 ounces or not uniformly distributed. Now, they don't look like they're uniformly distributed. Uniformly distributed means they're approximately the same number of babies on each of these intervals, and it looks like it looks more like a bell curve. It doesn't look uniform. But and a little bit later, we'll test whether they're normally distributed, which is it would be the bell-shaped data. But anyway, the first test we'll do is whether they're uniformly distributed. So the first step is to group the data into equal intervals so that there's an average of at least 5 births per interval. So I divide this into 5 intervals, so 50 to 69 ounces, we have 2 babies, a 54-ounce and 67-ounce baby. 70 to 89 ounces, that's rows 7 and 8. We have 6 babies, 72 ounces, 75 ounces, 83, 85, 87, 87. There's 6 babies, and so forth. 90 to 109 ounces, the observed value, number of babies is 21. 110 to 129 ounces, observed number is 15 babies. 130 to 149, 6 babies. And the expected values, if they're uniformly distributed, we have 5 intervals. 50 divided by 5 is 10. So the expected values, if H naught is true, would be an average of 10 babies for each interval. So then we can compute the test statistic. Each observed minus each expected, square it, divided by the expected. So we have for the first observed is 2. 2 minus the expected is 10 squared divided by 10. The second observed is 6. 6 minus 10 squared divided by 10. The third observed is 21. And then we have 15. And then we have 6. Okay, so 2 minus 10 is negative 8. Negative 8 squared is 64. Divided by 10 is 6.4. Okay, 6.4. 6 minus 10 is 4. 4 squared is 16. Divided by 10 is 1.6. 21 minus 10 is 11. 11 squared is 121. Divided by 10 is 12.1. And so forth. Add these up and we get 24.2. That's our test statistic. And then we need the critical value, which will be from the chi-square table. So we want to look in row k minus 1. There's k is 5 categories. K is the number of categories. 5 minus 1 is 4. And our alpha is our level of doubt, which is 0.05. We want 95% confidence, 5% doubt, so 0.05 of the chi-square table. So it's row 4, and column 0.05, and it looks like 9.48773, approximately 9.49. Okay, so our test statistic is more, 24 is more than our critical value of 9 point something. So that means we reject H naught with 95% confidence and conclude the birth weights are not normally distributed. And in fact, they don't look like they're normally distributed. They look more like a bell curve. I'm sorry. We conclude they're not uniformly distributed. In fact, they don't look uniformly distributed. They look like more like a bell curve. So we can also do a formal test of whether the birth weights are normally distributed. So H naught, so part B, I want to test H naught, birth weights are normally distributed. That means a bell-shaped graph, versus HA, birth weights are not normally distributed. And we can use the same confidence level. And again, we want to group the birth weight. For normal, to use a normal random variable, we need to fill in all the gaps. We'll do, for the first interval, instead of going from 50 to 69, we're going to go from anything less than 69.5 will be in the first interval. And the observed frequency is 2. So basically these are the same intervals as what we had before, but we just filled in the gaps. So we're going to have the same observed values. There's 2 that are less than 69.5 ounces, 6 babies between 69.5 and 89.5, and so forth. So those are observed values. The expected values, we have to use the z-table to get those. We have 50 babies. So the first expected value is 50 times the probability that x is less than 69.5. That's assuming a normal distribution. So we need to convert it into z-score by subtracting the mean, dividing by the standard deviation. I gave those to you at the beginning. You can also compute these, but if you put it in the data into your calculator. So I get the probability that z is less than negative 1.88. Actually, we need to look up, if we use the one-page z-table, we have to look up the positive 1.88 and subtract it from 5.5 to get a probability of 0.0301. Multiply that by 50, and that gives 1.505 babies. That's our first expected value. The second expected value, also multiplying the probability by 50 again, we have the probability that x is between 69.5 and 89.5, assuming x is normal. Compute it into the z-score by subtracting the mean divided by the standard deviation. So we get the probability z between negative 1.88 and negative 0.84. And we want to look up both numbers and subtract, look up both numbers in the table and subtract, and then multiply by 50. We get 8.52 babies. This is the larger probability minus the smaller probability. Actually, if you use our table here, this is going to be, those numbers will be a little bit different, but it's going to be, we'll end up with the same, it'll be the same answer, but the intermediate steps will be a little bit different. So if we look up 1.88, row 1.8, column 8 of the z-table, we get 0.4699. And then if we look up 0.84, row 0.8, column 4, you get 0.2995. and then if we subtract and multiply by 50.4699 minus 0.2995 equals times 50 equals 8.52. So it should be, these would be the numbers if you use the two-page Z table. You'd have these numbers here, but you could do it either way. But in any case, it comes out to be 8.52 babies. So that's the second expected value. The third expected value, again, you want to compute these into z-scores. This time we have z between a negative and a positive. So if you're using the one-page z-table for z between a negative and positive, you want to look up both numbers and add. So the 0.84 is going to be 0.2995. And then the 0.20, row 0.2, column 0.0793. And if you, so using the one-page z-table, you'd have those numbers. And if we add those numbers, multiply by 50.2995 plus 0.0793 times 50, 18.94. We still get the same answer. Okay, so here we have for E4, expected value 4, again, compute the z-scores. You get z between 0.2 and 1.25, and you want to look up both numbers and subtract. And so this be 50 times 1.2, column 5, 3944. Minus, these scores have the same sign, so you want to look up both numbers and subtract. 1.25, we did 1.25, 0.20, 0.0793. So if you use the one-page z-table, you would look up, subtract those two numbers, and 0.3944 minus 0.0793 times 50. 15.755 babies. The last expected value, probability z is greater than 129.5. So make it into z-score, subtract the mean, and this would be 0.5 minus probability, minus the number from the z-table, and multiply by 50, you get 5.28 babies. So those are expected values. We want to check that no expected values are less than 1, and that's true. None of them are less than 1. And we'll also check that no more than 1 out of every 5 expected values are less than 5. So I think we have exactly 1 of our expected values was less than 5, so that's okay, as long as we don't have more than 1 out of every 5. Okay, and then we want to compute the test statistic. Again, it's each observed minus each expected, square it, divided by each expected. So we plug in the numbers. 2 minus 1.505, square that, divide by 1.505, and so forth. Compute each of these terms and then add them up, we get a test statistic at 1.267. So the upper critical value, it's the same one we had before. It's row 5 minus 1, which is equal to 4, column 0.05 of the chi-square table. And our test statistic, 1.267, is smaller than the upper critical value of 9.488. And that means we fail to reject H naught. The sample does not provide enough evidence to conclude that birth weights are not normal. So this test can never prove that a variable is normal. It will prove with a certain level of confidence that it's not normal, or we don't know. And for this example, we don't know. So it's so this test is never conclusive. You're never going to prove that's normal using this test. You just prove that we're pretty sure it's not normal, or we don't know. Because the test is done with assumption, we're using the probabilities as if it's normal. So, you can't use that to prove that it's normal. Okay, another example. This is a multinomial. It's kind of related to the binomial. Binomial, you have two proportions, or two proportion favoring Biden, or the proportion not favoring Biden, or the proportion of heads versus the proportion of tails. But you could have more than one proportion. A die with 6 sides, numbered 1 through 6, was thrown 60 times. The observed outcomes are listed in the table below. So a 1 turned up 15 times, a 2 turned up 5 times, and so forth. We'll let P1 represent the proportion of 1s in the long run, P2 proportion of 2s in the long run, and so forth. And we want to test at the 0.05 level of significance. H naught, Pi equal Pj for all I and j. That means the die is evenly weighted, versus HA, Pi is not equal to Pj for at least some I and j. That means the die is unevenly weighted. Okay, so if the die is evenly weighted, then expected number to turn up heads, to turn up, each expected number is expected to turn up 60 over 6, which would be 10 times on the average. So the expected values are 10. And we want to check that no expected values are less than 1. That's true. No more than 1 out of every 5 expected values are less than 5. That's also true. So then we can compute the test statistic. Each observed minus expected, square it, divide by the expected. The first observed is 15. 15 minus 10 squared, divide by 10. Next expected is 5. 5 minus 10 squared, divide by 10. Next expected is, next observed is 12. 12 minus 10 squared, divide by 10. Then we have 7 minus 10 squared, divided by 10. 9 minus 10 squared, divided by 10. 12 minus 10 squared, divided by 10. So 5 minus 10 is 5. 5 squared is 25. 25 divided by 10 is 2.5. This is going to be 5 minus 10 is negative 5. You square the minus sign, it comes out positive. Negative 5 times negative 5 is negative 5 times negative 5 is also 25, and 25 divided by 10 is 2.5. 12 minus 10 is 2. 2 squared is 4. 4 divided by 10 is 0.4. 7 minus 10 is negative 3. Negative 3 times negative 3 is positive 9. 9 divided by 10 is 0.9. 9 minus 10 is negative 1. Negative 1 times negative 1 is 1. 1 divided by 10 is 0.1. And this one is going to be 0.4. So if we add these up, this is 5. This is 1. And we have 0.4 plus 0.4 is 0.8, so it'd be 6.8 would be the total. So the upper critical value is row 6 minus 1, which is 5, in column alpha of the chi-square table. So it's row 5 in column 0.05, I get 11.0705. Because our test statistic is less than the critical value, that means we fail to reject H0. The sample does not provide enough evidence to say the coin is unevenly weighted. Okay, so here's another example of a multinomial. The old drug cured 60% of the, or 0.6 of the patients. It reduced the symptoms of another 30% or 0.3 of the patients. It had no effect on 10% or 0.1 of the patients. So, so those are the old drug. We want to compare the new drug to the old drug. The new drug, we observed 56 patients were cured. Another 16 patients had reduced symptoms. 8 patients had no effect. So, so the total here is let's see, 24. Total is 80. Okay, so for the new drug in the long run, P1 is the unknown proportion that would be cured in the long run. P2 would be proportion that would have reduced symptoms. P3 the proportion that would have no effect. So anyway, and again, this is related to the binomial. This is the multinomial, but instead of just bi means two. That means two possible outcomes. Either you're for Biden or you're against Biden, or you're in favor of the death penalty or against the death penalty. So this is, but this is for free proportions. So we want to, at the alpha 0.05 level of significance, we want to test H0, Pi equal Pj for all I and j. The new drug is the same as the old, versus Ha, Pi not equal to Pj for some I and j. The new drug is different than the old. So the sample size n, O1 plus O2 plus O3 is 56 plus 16 plus 8 is 80. The expected values, if H0 is true, will be n for E1, the first expected value, n times O1, 80 times 0.6 is 48. E2, n times O2, 80 times 0.3 is 24. Now this is, these should be P's. Yeah, these are, I'll call these POs, PO1. P. The P, the proportion cured by the old drug, if we multiply that by the N, if the new drug is no better than the old drug, it should be N times 0.6 is 48 cured, N times P2, P02, 80 times 0.3 is 24, N times P03, 80 times 0.1 is 8. So those would be the expected. And then these up here, these numbers up here would be the observed. Okay, so then we can compute the test statistic, each observed minus each expected, and square it divided by the expected. So we'll have 56 minus 48 squared over 48 plus 16 minus 24 squared over 24 plus 8 minus 8 squared over 8. Okay, so this is going to be 56 minus 8 is 8. 8 squared is 64. 64 divided by 48. 1.3 and repeating 3's. I'll just put bar over 3. It's indicate repeating 3's. This will be 16 minus 24 is also 8. But this time we're dividing by 24. So this will be negative 8 times negative 8 is a positive 64. 64 divided by 24. 2.6 and repeating 6's. So I'll just put a bar over the 6. And this 8 minus 8 is 0, so that's 0. So if we add these up, we get our test statistic is 4. The upper critical value, we want to look in, we have 3 categories. 3 minus 1 is 2. So look at row 2, column 0.05 of the chi-square table, and we get 5.991 and 4.6. Okay. And because our test statistic of 4 is smaller than our upper critical value of 5.99, we fail to reject H naught. The sample does not provide enough evidence to conclude that the new drug is different. Okay, and that concludes this presentation.